Good evening to you all. Am I audible?
Yes, madam. Good evening.
Yes, okay. So today we are going to talk about now under this topic nanotechnology for textile and clothing. One of the very important type of a nanomaterial that we are going to discuss. So you all have already now have a proper idea about what nanotechnology is. What do you mean by nanoscale? When you compare the nanoscale to the other micrometer, millimeter, or even angstrom scale, where does the nanoscale stands? And also we have looked at what do you mean by nanotechnology? And what are the nanotechnology approaches, or what are the examples that we can take from the biology or the environment or the outside there? How does the nanotechnology has been applied in different areas, like in some animals, in some plants, leaves, and we have looked at that one. And also we have looked at why people use nanotechnology. Three main aspects we have discussed. And then we have looked at what are the techniques available, the categorization of the mainly. There are two categories of nanomaterial fabrication methodologies. So we have looked at that one. And also we have looked at dimensional wise, how does this nanomaterial categorization can happen. So dimension wise, zero dimension, one dimension, two dimension, and three dimension. So what are the definition of these dimensions? And then what are the different types of nanomaterials under these different dimensions? So that is what we have discussed during last two lectures. So today we are going to talk about one of the most important nanomaterial which can be used in different industries. So now y'all have heard about nanofibers. So if you take the dimensional categorization, the nanofibers are under the one-dimensional nanomaterial. It is because it's one scale is not in the nanometer scale where it is the length, but the diameter is in the nanometer range. So these nanofibers, there are different methodologies that we can fabricate nanofibers. And also there are different applications of nanofibers. So as students who have already learned about textile and different textile technologies, you all have heard about this term called fibers. So we all know fibers are the main building block of textile materials. So we do have natural fibers, we do have synthetic fibers, and we do have regenerated fibers. Right? So what do you mean by a fiber? You all can assemble these fibers together like in a staple fiber spinning operation, and then you can make a yarn. And out of that yarn, you can make a fabric or a textile material. So if you start with a filament fiber, you can assemble them together and then you can make a yarn and then you can make textile using different technique. And also maybe as textile technology students, you all have learned about how these non-woven mats can be made. So the today's topic, the nanofiber, we will be looking at two approaches that we can basically discuss about when we need to make nanofibers. So nanomaterial fabrication, there are two main categories how we can fabricate nanomaterials. The first one is top-down approach, and the other one is bottom-up approach. So in the top-down approach, you start from a bulk material, and then you basically um, you make them into small materials until you come up with nanoscale. Or else you can start with from the atomic scale, you assemble them, you make cells, you make cubes, you make crystals, you make molecules, and then you start assembling these things until you arrive at with nanomaterial. So that is the bottom up approach. So in this one, for the nanofibers also, there are two different ways that we can use to fabricate nanofibers. So the nanofibers can be done using a very interesting spinning methodology called electrospinning. So have you all heard about spinning before? So the spinning is to spin synthetic fibers or regenerated fibers. So this is not for the staple fibers or natural fibers. So how do they spin it? You have a polymer solution in the liquid form. So you can make this liquid polymer solution either by melting a polymer chips, or else you can dissolve polymer chips in different solvents, and then you can make a liquid polymer solution. And then you extrude it through spinneret. When you extrude it through spinneret, you have to make sure that you get the necessary molecular architecture in your fiber. So during this extrusion, it will decide how well the molecules are going to get oriented. And depending on that orientation, which is controlled by the drawing, it will decide what should be the diameter. And depending on the shape of the spinneret, it will tells you, or it will governs the cross-sectional shape of the fiber, which lead to different fiber or yarn properties. And then what you all have to do when this liquid polymer solution get extruded, you need to solidify this liquid polymer solution. This liquid polymer, you need to solidify it in the fiber format. So therefore, now if it is a molten polymer solution, what you all can do, we can have a cool airflow. So then once the temperature get reduced, it will start solidifying. So we call it as melt spinning. Or else you do have another two approaches for the filament fiber spinning operation, where now if it is dissolved in a solvent, you can either evaporate the solvent using a hot airflow. So we call this type of a spinning as dry spinning. And then the solvent can be removed by coagulating, or by coagulating this liquid polymer solution to a coagulation bath. We call it as the wet spinning. So that is how the fiber become, the liquid polymer solution become solidified. So if you take this very interesting procedure called electrospinning is somewhat like solvent spinning. So in the solvent spinning, you have the liquid polymer solution by dissolving the solid polymer in a solvent. So for the electrospinning also, if I describe the main or the general approach that we can understand, it is like a spinning method starting from a liquid polymer solution, and this liquid polymer solution will get dissolved in a solvent, right? So once it gets dissolved in the solvent, like in the normal spinning method, you do have a spinneret. But the thing is, this spinneret is little bit special. So you all can have a number of spinneret holes, or you all can have single. So in here, I have given an image of a magnified image of a syringe needle tip. So you all know these surgical syringes that we do have in pharmacies or at hospitals. They do have very tiny needle tip, which is highly electricity conductive. So this tiny spinneret, the tiny hole act as a spinneret, right? So like in the normal solvent spinning, you pass through this liquid polymer solution through this spinneret hole. And then what do you all do? You just dissolve, you let it get dry on a surface. The same principle like in a dry spinning method. But in here, it's a little bit different. It is because now if you start it from a needle tip, like given in here, it's in the millimeter or the micrometer range. But we need to produce nanofibers, which are in the nanometer scale of diameter. So therefore, this technique we call it as electrospinning, not like dry spinning. So the term implies the electrospinning. You basically use a electric field. So in this mechanism, not like in the normal dry spinning method, you do have the syringe needle tip and it can conduct electricity, and you do have the polymer solution here, and then you pressurize or extrude the polymer solution through this needle tip. So this needle tip being highly electricity conductive, this will get attached to a high voltage supply. So this is the ground and this is a positive or a negative voltage in kilovolts. So mostly it can go start from 10 kilowatt to 25 kilowatt. So imagine you give a very high voltage difference between the needle tip and a ground device. So what does it do? What you all have learned about electric field. So now when you give an high voltage difference without passing a current, it will create an electric field from the positive charge to the negative, to the relatively lower charge, right? So this is an electric field. What do you mean by electric field? A positive charge can get dominated at the needle tip, right? So once you have this polymer solution coming through this dermal tip, it will be held by the surface tension. So we all know when a droplet comes, it gets held by the surface tension. So if I try to magnify this one, this droplet try to be held from the dermal tip due to the surface tension, but it will have also a static positive charge due to the electric field that get applied. So if it has got a surface positive charge, if there is an electric field from the positive to the zero, so what does happen? This polymer solution tend to get extended through this electric field to this ground plane, right? So therefore, once this electrostatic force towards the other end of the spinning apparatus overcomes the surface tension. The surface tension is upward, electric field potential is downward. So once this start overcoming the surface tension, this will start ejecting like this. A polymer solution without much of a pressure will start ejecting. So this pressure or this force towards the collector plate is very high. So therefore what's going to happen? So even at this stage you all can see it's somewhere around like very minor micrometer scale, but still you all can see. And then because of the distance between the needle tip and the collector, now when this jet start ejecting, it won't follow a straight path. It will goes like a whipping action. Why does it do the whipping action? It is because of the surface charge. The bending will happen. It is because the repulsive forces on the surface of this fiber. So therefore you all can see, rather than going from here to here where the distance is x, it follows a comparably longer path. Why? Y is very much greater than x. So that means what? The same amount of material need to be stretched for a very long distance. So then what would you expect? The diameter of the fiber which get ejected from the needle tip tend to get very low, where it become to the nano level, and then you don't need a hot airflow, because once it's following this longer pathway, and since its diameter is very small, the surface area is very high, so therefore the solvent which dissolved the polymer solution tend to get evaporated without any force, and then it goes and gets solidified on a specific collector plate. So you all can arrange the collector plate depending on the arrangement of the fiber differentiation that you need to do. So therefore, if you have a look at the fibers that get collected to the collector plate, it basically shows a nanofiber mesh, something like this. Something like this. Okay. So that is the basic principle of electrospinning, right? So in essence, that is what we are going to discuss in detail in today's lecture, right? So if you take the web that get collected to the collector plate, so in this electrospinning, the yarn, the fiber diameter, and the mesh, we call that as a electrospun fiber mesh, and the porosity of that mesh, the texture, and if you want a pattern formation, like you don't need the fiber mesh like a mesh, but you need to arrange those nanofibers in a specific arrangement. So all these can be controlled, including the fiber diameter, the mesh size, the porosity, the texture, the pattern formation. Everything can be controlled by controlling different parameters of the electrospinning operation. Okay. So electrospinning is a major way to engineer without self-assembly. Like if you do not let it just go and deposit on a surface without self-assembly, you all can engineer the way you spin the nanofiber. Engineer means what? You control the parameters of the nanofiber mesh that you are going to collect. What are the parameters? Maybe the fiber diameter, maybe the uniformity of the fiber, the mesh size of the collecting sheet that you are going to have, the porosity of that one, texture, and some of those, like I have given you example, some of like these, some of the parameters can be controlled. Okay, so let's first of all try to get an idea about a feeling about the nanofiber, the scale. So we all know it can be categorized under the first dimensional nanomaterial. So the diameter is in the nanoscale, but for you all to understand the gravity of this nanoscale with the nanofiber, I have taken a very interesting example here. So if you take the distance between the Earth and the Moon, where I have given it like say 384,400 kilometers. So we are going to calculate how much of a gram of nanofiber is needed to fill this length from Earth to Moon. So how do we do the calculation? First of all, you think about the density of this material which we are going to use in order to spin the nanofiber is 1 grams per cubic centimeter. And if you think the nanofiber that we are going to use in this example is having a diameter around 100 nanometers, so we can calculate the number of grams that we need in order to fill the distance between 384,400 kilometers, right? So you substitute all the values here and it will shows you, if you go for the nanofiber scale, you need only 3 grams of this material, which makes the nanofiber a single nanofiber, and then using that 3 gram you can fill a distance somewhere around 384,400 kilometers. So just for y'all to get an idea about the gravity or the importance of the nanoscale. Okay, so in here I have shown you a few stages of electrospinning where the jet formation, we call this as the jet formation or else the electrospinning stages. So if you take this as the electric field, so at this stage A, you will see with the surface tension there will be a drop of the polymer liquid solution, and then once the surface tension, once the electric field overcome this surface tension, it will start ejecting, and then we call this as a tailor cone. The development, we call this as a tailor cone, And this is how the tailor cone get developed in stages during the electrospinning. So this is actually a magnified image of this electrospinning solution at this needle tip position. Okay, so this diagram is important. It is because it tells you what are the important things that you need to have for the electrospinning. You need to have a syringe pump in order to pressurize and send the polymer solution. And then you need to have a high voltage supply. Why do we need to have that? It is because this electric field is very important. And then you need to have a collector plate. Collector plate in order to collect the spun nanofiber. So this is the schematic representation of the electrospinning apparatus, which you should be very much thorough about, and you should be able to draw at least the very important information in a diagrammatic way, and then you should be able to explain how the electrospinning apparatus works. Okay. So if you look at the electrospinning procedure, so from the things which I have just explained, so it is very clear we apply a electrostatic potential using a high voltage supply unit between, we call the needle tip as the spinneret and the collector plate. So this collector plate can be of different forms depending on the texture, the shape, the alignment or the mesh size that we need in our spun electrofiber mat. Okay. And you need the electrostatic force and then you need the syringe pump system. So using the syringe pump system, a fluid is slowly pumped through the spinneret or through the needle tip. And then this fluid is usually a solution where the solvent can evaporate during the spinning, like in dry spinning in our normal spinning method. So when during the electrospinning, the droplet is normally at the start or at the beginning is held by its own surface tension at the spinneret tip until it gets electrostatically charged. So the polymer fluid which get held by the needle tip assumes a conical shape which we call it as a tailor cone. So once the surface tension of the fluid overcomes the electrostatic force, the droplet become unstable and a liquid jet is ejected. So that is the very initial stage or the starting point of the electrospinning. So the fiber formation, accordingly, we can divide it into very important three stages. So we call these as the stage 1, and then we call this as the stage 2, and then we call this as the stage 3. So what do you mean by stage 1? Stage 1 is actually, we call that the jet initiation. It is where the surface tension is overcome by the electrostatic forces and then it will just get ejected like a straight line. And then the stage 2, growth of electrical bending like in a whipping action. And then it goes a bending instability and whipping. So therefore the further elongation of this jet will happen like a drawing, and then you can have certain jet branching also depending on the spinning condition. And then the stage 3 is where you talk about solidification of these spun electrojet into a micro or nanofiber. Okay, so these three stages are very important when you are to describe about the nanofiber formation. So although you do not have to go through all these equations, but remember the stage 1, that is the jet initiation, right? It depends on these factors. A capital H, simple H, R, gamma, and a conversion factor. So what are these factors? The jet initiation or the stage 1 is governed by the distance from the needle tip to the collector, from the needle tip to the collector. And then the length of the liquid column, this length of the liquid column, and then the needle radius or the diameter, and then the surface tension of the solution. So these are some of the factors which governs the stage 1 of the electrospinning or the nanofiber formation. And then also, now in here, this is the jet initiation. And then the jet need to grows like this, right? So before the growth of electrical bending instability, that is this part, the tip accelerate this jet towards the collector plate. So this is due to the acceleration. This happens due to the acceleration. So this acceleration is very important parameter when it decide the nanofiber diameter. So this acceleration is controlled by these factors. What are they? The flow rate from the syringe pump, the surface charge, which is governed by the applied electric field, and the conductivity of the polymer solution, and the applied electric field. And if there is at least a milli or a microampere current passing through the jet, the density of the liquid, and also the initial radius of the jet. So these are the factors which basically controls the phase 1, that is during the stage 1, the acceleration of the straight. That why do we call this as a jet? It is because it is a straight line. Although you do not have to remember this equation, you need to remember these factors which controls the stage 1, that is the jet acceleration. And then the stage 2. So the stage 2 is where this bending instability happens. So as the diameter of the jet in the straight segment decreases monotonically with distance from the tip, the jet becomes very long and thin. So it is due to this whipping action. Why does the whipping action happens? It is because the excess charges. Now, when the fiber gets start ejecting, it has a surface charge, right? So if there's a bending, there will be more bending. It is because due to the electrostatic repulsion. So that is why without going like a straight line, it start bending due to the surface charge. Okay. So the location of excess charge within or on the fluid then tends to change with the elongation, bending and otherwise deforming the jet. That means the long jet become unstable due to the growth of various instabilities. Okay. So stage 2, if you do not control the stage 2, if there is an excess electric charge carried by the jet is reduced, the capillary instability Okay. So when the excess electric charge carried by the jet is reduced, the capillary instability which causes the cylindrical fluid jet to break up into droplets will occur. It is because now if you don't have the necessary electric charge, now this continuity will be broken. So therefore what happens? there will be droplets forming, and then these droplets will solidify as beads. So therefore, you can see if you do not control the flow rate accordingly, with the applied electric field and distance between the tip and the collector plate, the bead formation will occur, and this will basically be more prominent when the charge per unit area is small. When the charge per unit area is small, this bead formation can happen. Okay. And also you all can see these types of branching can happen. So these are not the usual format of a nanofiber mesh. So the branches is observed more frequently in more concentrated and more viscous solution. If you do have a very high concentrated and a very viscous solution in the electrospinning, so therefore the electric field, if the electric field is higher than the necessary electric field that we need, so therefore the jet formation can happen. Okay, so stage 3, that is the solidification. So during the process of jet elongation, the solvent evaporates. It is because it has a very high surface area and it leaves behind a charged polymer fiber. The solid polymer fiber are then deposited onto the grounded collecting plate or the screen. So during the fiber deposition process, a characteristic instability termed as buckling instability may occur due to the longitudinal. This because now when it comes and hit the plate, we call that as buckling instability occur due to the longitudinal. So when it comes and hit, there will be certain compressive forces to the fiber. Okay. And so therefore it get deposited into a fiber mesh. Give me 1 minute. So we call that as the buckling instability. And buckling instability is basically due to the longitudinal compressive forces from the jet which comes and deposit on the collector plate. Okay. So depending on the way that you want to collect these nanofiber, we do have different formats of the collector plate. So if you want to assemble, now in the previous case, you all can see it's not a line fiber. It's not arranged in a specific way. But if you want to align them, you can have these types of different formats of the collector plate. So you all can have a rotating drum. You can have a rotating wire drum. And then you can have a collector with a wire wound on that one. So I have given in each methodology, in each format, what are the advantages and what are the disadvantages when it's come to assembling of a line fiber mesh, right? So this continues like this. So y'all can a little bit go through the lecture note and learn advantages and disadvantages of these collection methodologies depending on the type of the collectors. So in this one, I have given you a scanning electron microscopic image of a line nanofiber sheet and a randomly oriented nanofiber sheet. So you all can see clearly the difference between the alignment and the random orientation. So randomly oriented fibers, so flat plate, or there are certain collectors which basically governs the random orientation. So these randomly oriented fibers provide high surface area compared to the others, and also it has a very good porosity. So therefore it can be used in filtration. So if you talk about the 3M mask, so the 3M mask has a randomly oriented nanofiber mesh, and it has the necessary porosity in order to filter even the viruses from the filtration. So randomly oriented fibers are also useful for blood vessel and tissue engineering because it's basically represent the human skin tissues or other membrane tissues in our biological system. So, but the random oriented fibers are not suitable to make yarns or for certain specific textile application because it doesn't have any alignment. So, therefore, you cannot expect the necessary strength and the uniformity in the mesh. So, comparably, I have given to you information about the aligned nanofibers. So aligned fiber orientation can also enhance mechanical properties if you want to make yarns out of that one, and it will improve the tensile strength and it will prevent the elongation of the mesh. So one application of this aligned fiber principle is where you can have these aligned fibers in a vascular graft. So these aligned fibers will prevent the sample from expanding significantly and will render the sample clinically sufficient to prevent burst and pressure. So in order to maybe replace certain blood vessels, so this is a good method. So processing aligned fibers. The most efficient and increasingly common method of collecting aligned fiber is by using a rotating drum collector. So the degree of the fiber alignment will be determined by the linear speed of the rotating collector. So if you increase the rotation speed, there will be more alignment. So in this one, this is the schematic diagram of the basic electrospinning setup for random orientation or aligned nanofiber collection. And then V, it basically shows how the surface velocity V in the circular rotating collector with a radius R will vary. Okay. So you can have different assembly system also depending on the design of the collector plate that you all are going to use. So I have given advantages and disadvantages of these also. And depending on different types of collectors, so these are some things which we can do. This is actually a vessel of polypropylene carbonate with a 2 millimeter inner diameter, which was done from certain assembling of the fiber during the collection. Okay. So this is another type of a structure of this fiber mesh. So I have told you like y'all can control the texture of the fiber mesh. So this is a honeycomb mesh structure that they have developed. So electrostatic charges on the deposit collector which prevents incoming electrospun fibers from depositing directly to the collector will form a honeycomb structure. So it's like just for you all to have an idea what are the engineering things that we can do in order to control the assembled or the deposited fiber mesh. And there is also another thing called needleless electrospinning. So candy floss machine, if you know, අපි අර මොකක්ද බොම්බෑ මොටයි කියලා කියන්නේ. ඒ හදන එකේ තියෙන මේ විදිය ප්‍රින්සිපල් එකක්ම තමයි you do have your solution and then you do have a porous electrospinning device and then you do have the cylindrical collector, you do have the electrode, and once you rotate this one due to the static charge that get developed between the solution and the electrode, you should be able to collect these nanofiber mesh, which is that the very common example of candy floss machine. So this is another type of a needleless electrospinning. You do have the saw teeth collector, and then through a magnetic field is not through a electric field. So therefore these jets will get initiated and then it will go and deposit on the saw teeth collector. Okay, the spinneret modification. So you can have coaxial spinneret like this. So coaxial spinneret, single fibers made out of two different materials can be electrospun. Hollow fibers can be fabricated by removing the core material. So materials normally not electrospinnable can be made to nanofibers by using electrospinnable outer materials, so that is one of the advantage. So the materials to be electrospun must be chosen carefully to reduce mixing of the material in co-spun electrospinning. So this is actually the spinneret modification. Okay. Gas jacket electrospinning, single fiber made out of two different materials can be electrospun by modifying the spinneret. And materials to be spun in here also, if it is a coaxial or a gas jacket electrospinning, you need to make sure the two materials won't get mixed during the spinning. And this is also something very important. So there are various parameters that basically governs the electrospinning operation. So the electrospinning process is solely governed by many parameters which heavily affect the fiber morphology or the shape and the diameters. So we normally classify these parameters into three separate sections as solution parameters, process parameters, and ambient parameters. So what are the solution parameters which governs the spun fiber morphology and diameter? The molecular weight of the polymer solution that we are using, the concentration of the polymer in the liquid medium, the viscosity of the molecular solution, the surface tension of the molecular solution, and the conductivity or the surface charge density of the polymer solution. So those are the solution parameters which governs or controls the electrospinning operation. And then we do have process parameters, which are the applied voltage, flow rate, type of the collector, the tip to the collector distance, and diameter of the tip. So all the parameters other than the solution parameters during the electrospinning are under the process parameters. And then we do have ambient parameters or the atmospheric parameters as temperature and humidity, which basically controls the electrospinning operation. So let's say how each of these parameters controls the fiber morphology and the diameter. So if you take the solution parameter concentration, so the electrospinning process for fiber formation to occur, it need to have an optimum solution concentration. So it should exceed the minimal concentration and also it should not exceed a maximum solution concentration. So if you do have a low solution concentration, you should be expecting these types of bead formation. So once the solution concentration increases, the shape of the bead changes from spherical to spindle-like. And finally, the uniform fiber with increased diameter are formed because of the higher viscosity resistance, because the concentration is directly related with the viscosity. So if the concentration of your liquid polymer solution is lower than the minimal concentration, beads may start occurring. So if the concentration is greater than the maximum concentration, the formation of continuous fiber cannot be done because it cannot maintain the flow of the solution. So therefore, you should be expecting large fiber formation. So another solution parameter is the molecular weight, and this actually has a high impact on the rheological and electrical property. What do you mean by rheological property? The flow property. Like viscosity, surface tension, we call them as rheological property. And electrical property, right? Conductivity, dielectric strength, likewise. So the molecular weight basically controls the rheological property of the polymer solution and electrical property of the polymer solution. So this parameter, the molecular weight, affect the morphology of the electrospun fiber. So the molecular weight polymer solution have been used in electrospinning as they provide the desired viscosity for the fiber generation. It's been observed that if you do have too low molecular weight, then the bead tend to form because there are no continuity. If you do have a high molecular weight, so therefore it can gives you large average diameter because the higher molecular weight increase the viscosity. So the molecular weight of the polymer reflect the number of entanglements of polymer chains in a solution. So if there are more entanglements, the viscosity is very high. So therefore it will lead to large average diameter of the spun fiber. So the high molecular weights are not always essential specifically for electrospinning, not like in other spinning method. If there are sufficient intermolecular interaction within the solution, the entanglements are sufficient enough, it can provide a substitute for the interaction connectivity which can be obtained through chain entanglement. So therefore, in principle, you don't have to have a very high molecular weight like in the normal spinning operation, but you need to have the necessary molecular entanglement. So therefore, the necessary molecular weight need to be there. And then viscosity is another solution parameter. So the solution viscosity is very important, determining the fiber size and the morphology. So it exists the polymer specific optimal viscosity value. So the concentration, the molecular weight basically governs the viscosity. So if you use a very low viscosity, then there are no continuation of the fiber. So therefore the bead may form. So therefore the optimal viscosity need to be maintained. If the solution viscosity is strongly related to the concentration of the solution, so it's the same observation that we can give for the viscosity like in the concentration. Okay. And then what about the surface tension? Uh, the solvent composition of the solution. What type of a solvent that we are using? What is the concentration of the solvent? Depending on that, it will control the surface tension of the liquid polymer solution. So the high surface tension of a solution inhibits the electrospinning process because it is unstable, the jet is unstable, so it generates the spraying of the droplet. Solvent එක surface tension එක අඩු වුණොතින් spray වෙන්න පටන් ගන්නවා solution එක rather than forming fibers. So the formation of droplets, beads and fiber depend on the surface tension of the solution, and lower surface tension of the spinning solution help electrospinning to occur at a lower electric field. So we all know for the jet initiation to happen, the electric field needs to overcome the surface tension. So, however, not necessarily a lower surface tension of a solvent will always be more suitable for electrospinning. Not very high surface tension, lower surface tension is preferred. Why it is that? It is because the surface tension determines the upper and the lower boundaries of the electrospinning window if all other variables are held constant, all other parameters. And another solution parameter is the conductivity or the surface charge density. So polymers, most of them are conductive, with some of them are having very Some of them are having some limitation in the dielectric constant of the material. Okay. So the solution conductivity is mainly determined by the polymer type, the solvent that we are using, and the availability of ionizable salt. So it has been found that within the increase of electrical conductivity of the solution, there is a significant decrease in the diameter of the electrospun nanofiber. Whereas if you do have a low conductivity of the solution, there will be low elongation. It is because it is a surface charge dependent phenomenon. Okay. So highly conductive solutions are extremely unstable in the presence of strong electric field. So you need to have this connected with the electric field. So which results in a dramatic bending instability as well as a broad diameter distribution. So in general, electrospun nanofibers with the smallest fiber diameter can be obtained with the highest electrical conductivity, and it has been found that there is drop in the size of the fiber is due to the increase in electrical conductivity. If you do have high electricity conductivity in your polymer solution, it will reduce the fiber diameter. And you all can control that by dissolving ionic solutions. Okay, so then it will control the dielectric charge in the polymer solution. And then voltage is actually a process parameter. So you all can see we can expect the diameter to be reduced once you keep on increasing the voltage, but there is a limitation, right? So only after attainment of the threshold voltage, the fiber formation start occurring. So it's actually type of a trial and error method where you need to check all these parameters, how they are linked together. It is a trial and error process. The flow rate or the injection speed. So if the flow rate get increased, the diameter of the fiber, we can expect an increase in the diameter. The lower feed rate is very good as the solvent will get enough time for the evaporation. So there should be always a minimal flow rate for the spinning solution specifically to produce not microfibers but nanofibers. So the high flow rates results in beaded fibers due to the unavailability of the proper drying. If the flow rate is high, then the collection speed, so therefore the beads may form. And the tip to collect the diameter, it's so obvious if you let more distance for the drawing operation, it will produce comparably low diameter fiber. Okay, so it's been found that a minimal distance is required to give the fiber sufficient time to dry before reaching the collector. Otherwise, with distance that are either too close or too far, beads can be observed. It has been reported that flatter fibers can be produced at closer distance, but with increase in distance, round fibers can be observed. And the type of the collector, yes, we know, depending on the shape and the type of the collector, we can have a lined or randomly oriented fiber. And the humidity and temperature, which are environmental parameters. So if you do have a low humidity, then the volatile solvent may dry rapidly. So sometimes evaporation, if it is so fast, then compared to the removal of the solvent from the tip to the needle, and this would create a problem in electrospinning. So that means if the evaporation rate is too fast compared to the removal of the solvent. So therefore there could be certain repercussions. The electrospinning process may only be carried out for a few minutes before the needle tip is clogged. It is because at the tip it is a very fine tip. It can get clogged if the evaporation rate is too fast. The temperature, so an increase in the temperature will decrease the fiber diameter. It is because it will decrease the viscosity. At higher temperature, it will decrease the viscosity. So therefore, you can expect an decrease in the diameter. So the things which was discussed, the solution parameters, the process parameters, and the ambient parameters, and how they affect the fiber morphology is tabulated in this table. You all can refer to this one. So I have given common type of polymers, their solvents, and the concentrations that we can use. And if you spin nanofibers, what are the applications? So it's tabulated in here. Okay. So the nanofibers, the beauty of the nanofibers, it has a very high aspect ratio. The diameter length ratio is very high. Aspect ratio is diameter to length ratio. So you all can see, if you take a diameter of the fiber, starting from the micrometer scale, the specific area of the fiber will get increased. Linearly, it get increased. Right? And that's actually for the solvent electrospinning. There's another thing called melt electrospinning. So the melt electrospinning, it actually will allow you to produce nanofibers in a variety of applications. Why? It is because it can overcome certain technical limitations in the solvent electrospinning. So in melt electrospinning, instead of a solution, the polymer is melt and then introduced to the capillary tube and need to be performed in a vacuum condition, not like in a normal ambient condition. And for that, the capillary tube, the traveling of the charge melt fluid jet, and the metal collecting screen must be encapsulated within a vacuum. So there are advantages and disadvantages over the solvent electrospinning. So advantage, so obvious, melt electrospinning, it doesn't need a solvent to dissolve the polymer. So you can expect higher production with no loss in mass by the solvent evaporation. And generation of sub-micron scale fibers of polymers which lack appropriate solvent at room temperature can be overcome by following this methodology. And it is comparably a cheaper procedure to the solvent electrospinning. What are the disadvantages? Yes, it do have high viscosity. You cannot control the viscosity by controlling the concentration. So it required higher processing temperature and you need to maintain that temperature throughout the spinning. And then most of the time the melt electrospinning, it does not allow you to form the nanometer range. So therefore the melt electrospinning is not widely used for the nanofiber formation. Okay, so for the melt electrospinning, these are the materials and their processing temperatures. So the characterization, how do you characterize the electrospun nanofibers? So the physical and the structural properties can be characterized, mechanical properties can be characterized, and chemical properties can be characterized. So if you take the geometrical characterization, it is the shape and the diameter, the fiber orientation, the morphology, these can be basically characterized using microscope. What are the microscope? Scanning electron microscopy can be used, transmission electron microscopy can be used, and also atomic force microscopy can be used. And also the porosity of the fiber mesh is another geometrical characteristic, and the porosity can be measured using BET type of instruments, BET instrument. The chemical characteristic is basically the presence of the solvent on the deposited fiber mesh. What are the functional groups on the fiber mesh can be done using molecular structure characterization, can be done using two analytical technique called Fourier transformed infrared spectroscopy and nuclear magnetic resonance technique, NMR technique. Right? So the mechanical characteristic, that's the surface tension, the impact resistance, the tensile strength. So see, being a nanofiber, you cannot handle it. You cannot see it through your naked eye. So therefore it need to be done through specific devices like nano indentation, bending test, resonance frequency measurement, microscale tension test. So these are the specific analytical methodologies that we can use to mechanically characterize the nanofiber. Right, so these are some of the results that was obtained by mechanical characterization of specific nanofibers. So what are the variables in electrospinning? Chemical composition, polymer molecular weight, the solvent qualities, and the processing variabilities can be the applied electric field, the distance between the tip and the collector. So these are some of the electrospinning variabilities, and in here I have given an example, the molecular weight and how frequently we use this molecular weight to spin electrospun nanofibers. Normally, the molecular weight somewhere around less than 10,000 need to be used for it to be suitable for the electrospinning operation. And electrospinning application, this is one of the most important topic in electrospinning. So I have listed few of them. So you need to know in detail what are these application and how it is important in the textile and other industries, right? So now, up to now, do you all have any questions? Up to now, do you all have any questions? ප්‍රශ්න තියෙනවද ඔයගොල්ලන්ට අහන්න? Okay, since you all have not seen the electrospinning apparatus and you all have not experienced or you all have not observed how does it happen, let me share a few video clips with you. So please pay attention to these video clips because it will demonstrate how the electrospinning can be done. There are a few interesting videos. Give me 1 minute. So this video will demonstrate the basic setups of a electrospinning apparatus. Let's have a look at that one. I hope everyone can see the screen. Just illustration. Okay. So this is an
Electrospinning.
that they have used in order to spin polyvinyl pyridine electrospun solution. Let's have a look. Can everyone see the screen? Can you all see the screen?
Yes, madam.
Okay. So this is an actual experiment which they have conducted in order to spun polyvinyl pyrrolidine electrospun nanofibers. Okay.
Electrospinning is the method of using high voltage to produce ultra-small diameter fibers. In the electrospinning process, a polymer solution is held inside a syringe needle pump. A high voltage power supply is used to create a charged jet of polymer solution. When this jet travels in air, the solvent evaporates and leaves behind a charged fiber. Because of the intense electric field that exists between the needle tip and rotating collector, the fibers are electrostatically elongated and collected on the metal sheet. The apparatus used in the electrospinning process is shown here. The hardware consists of high voltage power supply, syringe pump, and collector assembly. In the rest of the video, I will go over each sub-assembly and demonstrate how the electrospinning machine operates. Let's first go over the drum collector assembly. The drum collector is detachable and it is driven by a DC motor. To install the drum collector, align the gears and insert it gently in place. Place the collector assembly on top of the aluminum base. Connect the DC motor to the controller. Plug in 12 volt and provide power to the control panel. Turn on the collector motor. The collector rotation speed can be adjusted by turning the dial on the control panel. In this section, we will illustrate the syringe pump usage. On the control panel, push the switch upward to reverse and turn on the telecom motor switch. The pump motor will rotate at maximum speed when traveling in the up direction. After the highest position is reached, carefully remove the syringe from the white tube housing. When you are ready to run experiments, fill the syringe with liquid sample. For alignment purposes, install 2 O-rings as shown. This particular syringe size is 10 cc. Insert the plunger end of the syringe into the white tube housing. Then lock the syringe by placing the hand tab into the slot. Set the pump direction to dispense and turn on the pump. When the pusher inside the white tube is engaged with the syringe plunger, liquid droplets will form at the tip of the needle. Dispense speed can be adjusted using the potentiometer located on the control panel. Connect the high voltage clip to needle. Warning: make sure the high voltage power supply is off before touching the clip. Let's now go over the high voltage section. LabMate is an adjustable high voltage switch mode power supply. It is compact, lightweight, and versatile. Your front panel control for the generator are as follows. Voltage displayed in 5 digits. Voltage adjustment dial with turn counting indicator. Remote control receptacle. Indicator light when the unit is under remote control. Indicator light when output is in constant current mode. Current display. Current adjustment dial. High voltage on-off switch. On the back of the generator you will find M5 threaded stud for grounding. Main power on-off switch. DC input connector. High voltage output connector. Now that we have gone over the basics of the high voltage power supply, let's complete the setup by going over the high voltage connection. Proper grounding is very important. Make a secure ground connection between the high voltage power supply and earth ground. Make the 24-volt connection. Connect the high voltage power supply to telecone tower.
See how do they do that? So this is, they do have this needle tip connected to
The
the
electrospinning machine is ready for demonstration. Depositing the electrospun fibers on an aluminum foil works well because it is easier to gather samples with different parameters that you can go back to analyze later. You can see here that we're using double-sided tape to hold the aluminum foil in place. Wrap the foil around the drum collector. Try to keep it tight and cut off the excess foil. After the metal foil wrapping is complete, put the drum collector back in place. From the control panel, set the syringe pump flow rate and collector speed. After that, turn on the motors. On the high voltage power supply, adjust the current setting to the smallest output value that will work for your setup. In this particular demonstration, electrospinning did not require any current output, so the current limit was kept below 0.1 milliamp.
Still it is not spinning.
This will limit the current output in case there is a short. Next, set the high voltage using the dial indicator. When everything is in place,
now
turn on the high voltage output. Observe the electrospinning action and adjust the high voltage value, collector speed, and pump flow rate to get the desired result. Electrospinning is a fascinating fabrication technique. With a small benchtop setup like the one you've seen, you can do a lot of interesting research and development. Do you have a material you want us to electrospin? You can leave the material suggestion in the comments.
So this is another one about the coaxial electrospinning which we have discussed.
The power to enjoy my life, now in my hands.
Do you want to live the Australian dream? Do you love working with children?
Spinneret with two concentric. Welcome to Spruce Science. Today, we're excited to introduce you to our coaxial electrospinner and its spinneret with two concentric needles. You will see how we use the coaxial electrospinner to create electrospun fiber mats with red markers. This capability has exciting potential for targeted drug delivery systems, such as using electrospun fibers loaded with therapeutic drugs for wound dressing. We can't wait to show you the final result, so stay tuned. In the rest of the video, we will first provide an overview of the hardware we will be using. Then, we will move on to demonstrating the coaxial electrospinning process in detail. Get ready to see the magic of electrospinning in action. Gathering the electrospun fibers is made easy with the use of the collector. The rotation speed of the collector is adjustable, allowing you to fine-tune your process to achieve the desired results. The assembly is user-friendly and provide a convenient way to collect your electrospun fibers. The coaxial spinneret is a unique tool that allows you to mix and match two independent flow paths through its two concentric needles. These flow paths come together at the tip, providing endless possibilities for creating a variety of fibers. The two syringe pumps that are used in the electrospinning process are independent and have been designed to be electrically insulated, allowing them to withstand high voltage. The controller, with its analog interface, allows you to have intuitive control over the collector and syringe pumps. The adjustable high-voltage power supply is a key component of the electrospinning setup, giving you complete control over the output. You can switch between constant voltage mode and constant current mode to suit your specific needs. This particular model can deliver a powerful 30 kilovolts, which is a great range for electrospinning applications. The current output limit is 400 microamps, which is more than sufficient for the electrospinning process and ensures that you have a good fit for your application. To connect the high voltage output to the sample, we will be using the hook clip. Just a friendly reminder to always verify that the high voltage is off and fully discharged before touching any of the equipment. We're going to demonstrate how to use the coaxial electrospinning machine to create compound fibers. To begin, we will use the main syringe pump to deliver a solution of PVP polymer to the center needle. Then, we will use the second syringe pump to deliver red ink to the outer needle. When the two elements meet at the tip of the coaxial spinneret under the influence of high voltage, they will combine to form a PVP fiber mat with red markers. This process is driven by an intense electric field, which transforms the polymer solution into fibers as they travel through the air. It's an exciting and simple way to create unique and functional materials using electrospinning. Stay tuned to see the final result of our compound fibers. We are briefly going to talk about the many benefits of using PVP in your electrospinning process. PVP is a synthetic polymer that is soluble in water and alcohols, making it easy to work with and form into films. It attracts and holds on to water molecules from the surrounding environment and has good wetting properties. PVP is a versatile material with high heat resistance and good adhesive properties. It is also non-toxic and acts as a good dispersing agent, helping to prevent settling and clumping of solid or liquid particles. These characteristics makes PVP an excellent choice for a variety of applications in electrospinning. As you can see, the fibers gathered on the collector has a stunning light pink color. Upon closer inspection, you can see that the red ink is uniformly dispersed throughout the mat. It's truly a sight to behold. Everything was going smoothly during the process, but once we turned off the high voltage power supply, a droplet formed at the tip of the needle. As it dripped down onto the fiber, it created a hole in the mat. It's important to be mindful of these potential issues and to have a plan in place to address them. The electrospun PVP mat with red marker has a fibrous structure and can be easily removed from the collector.
This sheet has many millions of nanofibers in it.
This amazing technology allows us to inject one solution into the other at the tip of the needle, where fibers are drawn under an intense electric field. This gives us the flexibility to create a variety of fibers, including coaxial fibers, hollow fibers, compound fibers, or any combinations that we desire. This technology can be utilized in the medical field to deliver therapeutic drugs directly to targeted cells, tissues, or organs. One specific application is the use of PVP fiber mats as wound dressings, as they can help to maintain moisture around wounds and can be enhanced by the addition of therapeutic drugs. Electrospinning has the potential to greatly improve wound dressings through its ability to precisely deliver particles, molecules, or liquids to carrier fibers. This combination of moisture retention and targeted drug delivery can greatly improve the healing process for wounds. Thanks for joining us today. If you have any thoughts on the future of electrospun nanofibers in the medical field, or if you work in the industry and can share some insights with us, please leave a comment below. We would love to hear your perspectives. Don't forget to visit our website for more information. And if you want to show your support.
Okay. So those are the demonstrations which I have to show you all. Do you all have any questions up to now? Okay, since now we have already covered 3 lectures, now we do have 30 more minutes. I want to share this small questionnaire with you. You can start answering the questions, and then maybe I will leave somewhere around, since we do have 30 minutes more. Yes, in this question paper, there are 40 MCQs and there are a few structured questions as well, maybe 1 or 2. So I will share this question paper with you. You need to answer it within the time given. Until 8:30 we do have time. And then before the session end, you need to send me your answer sheet in this Word document. Write in your index number. Okay, please send it me via message, WhatsApp message. No, sorry, not WhatsApp message, Zoom. Zoom එකේ තියෙන message platform එකෙන් මට මේකේ answers ටික ඔයගොල්ලෝ එවන්න ඕනේ. Okay. Let me share that with you. So this is based on the lecture 1. Okay, I hope everyone can see the Word document which I have shared with you all. Please answer the MCQ questions and then send me your answer sheets. I can share the first lecture notes with you in here. So the lecture 1 lecture notes are also shared in the Zoom. Okay, you can start answering. So do you all have any questions that need to get clarified? ප්‍රශ්න මොනවාරි තියෙනවද clarify කරගන්න ඕනේ. Question paper එක ගන්න පුළුවන් නේද? අප්ලෝඩ් කරගන්න, ඩවුන්ලෝඩ් කරගන්න පුළුවන් නේද? Is everyone here? Okay. Try to answer the questions. I need your answer sheets. How many of y'all have finished at least 10 question answering 15 questions? Please raise your hand. Jitmi, are you attempting the... Okay, Jitmi raise hand. Ashini? Okay, Risky? Are you attempting the questions?
Yes, madam.
Okay.
madam structured question වලටත් answer කරන්න ඕනද?
ඒ ටික තියලා තියන්න MCQs ටික answer කරලා ඉවරද?
නෑ madam තාම.
Okay, once you're done, please send me the answer sheet via message. Structure ටික ඕනේ. I have got only 2 answer sheets. Can others please share me the answer sheets? Okay, so I will send you my email address. Please share with me your answer sheets before අද ඉවර වෙන දවස් ඉවර වෙන කලින් මට answer sheets ටික එවන්න මම number එක මගේ email address එක share කරන්නම්. Has everyone got the email address? Okay, y'all can send the answer sheets to this email address. We'll wind up for today. Please send me your answer sheet before today. And I will meet you all on next Tuesday. Next Tuesday, 6:30 to 8:30, or yes, we can meet 6 to 8. 6 to 8. Is the timers given as 6 to 8 or 6:30 to 8:30? Tuesday? You can join the lecture at 6 o'clock next week, Tuesday. Okay, thank you all. Have a good night.